Then thank you again for the opportunity to talk with you today. I'm really looking forward to sharing with you some new information, some new research into the nature of cosmic acceleration. And I'll also tell you a lot about a new scientific instrument called the Dark Energy Spectroscopic Instrument, or DESI. I'm going to talk about DESI in particular because I've helped to build the DESI instrument over the last 5 years. And I'll be telling you why we built it. And I'm especially excited because DESI is just about to begin a new survey of the night sky that should dramatically surpass similar projects and hopefully will help us unravel the mystery of cosmic acceleration.
Hello, ¿cómo te va?
Hello?
¿Cómo te va?
Let me see what I can do about that.
How does it?
I'll show you my shoes.
Yeah, I can see it. Where?
Look at my shoes.
Maybe some.
Oh man, that's a big
that
tooth.
would be
There we go.
great. Okay. Thank you.
Sorry about that.
Right. So I chose this background image for my title slide for 2 reasons. One is that it captures the impressive structure that houses the telescope. DESI uses the largest telescope at the Kitt Peak National Observatory in Arizona, the 4-meter Mayall telescope, and it appears to both tower over the other telescopes and also nearby mountains. As I expect this audience knows well, the Mayall telescope was only the 2nd largest telescope in the world when it was completed in 1973, thanks to a certain 5-meter telescope that saw first light in 1949. But for those of you who have been in the Hale Dome, it may be useful perspective to know that the Mayall is only about 20 to 25% smaller than the Hale telescope in a number of respects, including the size of the mirror, the size of the dome, and the moving mass of the telescope and dome structure. Another key difference is that the interior of the dome for the Mayall is about 120 feet above the ground level. So about here, if you can see the pointer that I have on the screen, and that the entire observatory structure is equivalent in height to about an 18-story building. And this was to bring the observatory up above the local turbulence in the ground and to bring it more up into the smooth air blowing over the sites to improve the image quality. But I also chose this photo because it captures some of the beauty of the sky at night. One of the most romantic aspects of astronomy is spending the night at a telescope, usually at the top of a mountain in some very secluded location, staring up at the night sky, and just pondering the sheer size of the cosmos relative to our very small place within it. This contrast is humbling, no matter how impressive the telescope and the mountain may be. To better capture this point, I'd like to share with you a small anecdote about the immensity of the universe. You may have heard of the New Horizons mission to Pluto, which was launched in 2006. At the time, New Horizons was the fastest spacecraft ever launched from the Earth. When it flew by Pluto, 10 years later, it was traveling at 32,000 miles per hour, or about 14.3 kilometers per second. That's amazingly fast, yet at this speed, it would take nearly 90,000 years to reach even the nearest star. And the objects that interest me and that I'll be talking about today are millions to billions of times even farther away. Yet it was neither the beauty of the night sky nor the vastness of the universe that attracted me to astronomy. Instead, I was attracted by the possibility that we can use astronomical observations to study physics and answer questions about the universe. Even though the objects we study can be millions to billions of light years away. And therefore, they must have emitted the light we see today millions to billions of years ago. One early, very relevant application of using astronomical observations to study physics is Edwin Hubble's discovery that more distant galaxies are receding from us more rapidly. This figure shows the key result from Hubble's work, which was published in 1929. The bottom axis shows the distances to various galaxies, in his study, astronomers commonly measure distances in parsecs, which corresponds to a little more than 3 light years. And for context, the nearest star to the Earth is a little bit more than 1 parsec away. The galaxies on Hubble's diagram are at distances of up to about 2 million parsecs. They are already huge distances, much larger than our entire galaxy. The vertical axis is the recession velocity in units of kilometers per second. These range up to about 1,000 kilometers per second. And these are huge velocities, much faster than New Horizons' speed of only 14.3 kilometers per second when it passed Pluto. The light waves from objects moving away from us are shifted to longer wavelengths by the Doppler effect. This is similar to how sound waves from a siren speeding away from you will be shifted to lower frequencies. Because red light is the longest wavelength electromagnetic radiation that the human eye can see, astronomers say objects moving away from us are redshifted. The key result of this figure is that more distant galaxies are more redshifted than near objects, and specifically that the redshift is proportional to the distance. This means that the universe is expanding. To help picture why this is the case, imagine the 3D universe as a 2-dimensional sheet. This is just an approximation, just like you can only see me in 2 dimensions, even though I'm quite sure that I am 3-dimensional. So imagine the universe as a stretchable sheet with galaxies painted on it, and then imagine stretching the sheet to make it larger. Here is a visualization to help. The bottom of the slide is supposed to represent the start of the universe's expansion in the Big Bang nearly 14 billion years ago. Then the 3 subsequent layers are later times in the evolution of the universe. At each later time, the sheet has expanded. The distances between neighboring galaxies have steadily increased, and the further away galaxies were initially, the more they have moved apart. Since more distant galaxies have separated by a greater amount, they must also be moving farther apart more rapidly from one another. That is why there is a relationship between distance and redshift. Another thing to note is that while the universe has expanded, the galaxies have not expanded by a similar amount. This is because gravity is holding them together in spite of the expansion of space around them. Now I want to go back to Hubble's diagram to emphasize several important aspects of it. The first is that the relationship between distance and redshift is not overwhelmingly obvious. In statistical terms, the data are pretty noisy. One reason for that is that the measurements were hard to make. The observations Hubble used were obtained with photographic plates, which were not as sensitive as modern detectors, and they were much, much harder to calibrate. Another is that 2 million parsecs is not really a big sample of the universe, even though light from that distance has been traveling to the Earth more than 10 times longer than the oldest fossil evidence of our species. At small distances like these, the redshift measurements are affected by the random motions of galaxies, in addition to the expansion of the universe, and they only sample a very small fraction of the entire age of the universe. The second part I want you to take note of is that this only has about 30 measurements on it total. In the 92 years since this figure was published, the relationship between distance and redshift has remained a fundamental tool of cosmology. The slope of this relationship is called Hubble's constant in his honor. Hubble's diagram demonstrated conclusively that the universe was not static, which until that time had been widely believed. Many subsequent studies have used the distance redshift relation to estimate the age and mass density of the universe, and now we use it to study cosmic acceleration as well. To picture how the distance redshift relationship can be such a powerful tool, imagine that you were on Earth, that part should be easy, and that you also throw a ball up into the air. Also not too hard to imagine. If you throw a ball straight up in the air, It is moving the fastest just when it leaves your hand. That is the initial speed. Then, as it climbs higher and higher, the speed decreases. In astronomical terms, the expansion rate decreases with distance, and the ball is slowing down the longer it is in the air. The reason it slows down is almost entirely due to the gravitational attraction between the Earth and the ball. We're ignoring air resistance. This is analogous to how we expect the expansion rate of the universe to decrease as the universe expands. To think about that a little bit more, now imagine that you were on the moon and threw a ball into the air with exactly the same initial speed. The ball would slow down more slowly because the force of gravity is weaker on the moon. The lower mass of the moon is why there would be a different relationship between the speed of the ball and its distance from you. And on the moon, you wouldn't have to worry about air resistance, although you would have to worry about breathing. That is why scientists like to use thought experiments when possible. They're usually safer than real ones and a lot cheaper. In the local universe, where Hubble made his first measurement, he did not see a change in the expansion rate. This is because his data were not good enough to see the effect. But cosmologists knew the universe was full of matter, and they knew about gravity. So they expected to see a gradual slowing of the expansion rate if they could measure objects at greater distances, and if they could make more accurate measurements. To make distance measurements more accurately, astronomers use two classes of methods. One class is called a standard candle, and the other a standard ruler. The basic idea behind both the standard candle and the standard ruler are pretty similar, and both are illustrated by this picture. We identify some standard object whose intrinsic properties we know, such that when we observe them at some unknown distance, we can figure out how far away they must be. For example, imagine we knew two candles were identical. If one of them appeared fainter than the other, we would know the fainter one was farther away. Similarly for a standard ruler. If we knew a collection of rulers were identical, we would know that the ones that look smaller, which means they have smaller angular sizes, must be further away from us. Using very well-calibrated equipment, we can use these tools to estimate distances very well. Of course, since we're observing objects at astronomical distances, we need our standard candles to be very bright and our standard rulers to be very big. Fortunately, pretty good proxies for both exist in nature. The standard candle that we use is a special variety of exploding star called a Type 1a supernova that can become as bright as an entire galaxy. They're so intrinsically luminous that astronomers have detected them more than halfway across the universe. From careful measurements of how the brightness of these supernovae change over time, it is possible to infer their distance. The standard ruler that we use is called the Baryon Acoustic Oscillation Scale, which I'll return to later. Needless to say, it is much bigger than any ruler you can buy on Earth. It's even much bigger than our entire galaxy. Before I describe some of the results of work with supernovae, imagine yourself again on the Earth throwing a ball into the air. We all know to expect that the ball will slow down as it climbs higher and higher. And we know that the force of gravity is acting in the opposite direction of the ball's motion. Now imagine your surprise if the ball stopped slowing down and instead started to speed up and fly away from you faster and faster. What would you say? If I saw this happen, I'd have a hard time believing my eyes, as it violates the laws of physics I learned about in school. Actually, I'm sure I would have had a hard time believing this even if I hadn't studied physics. It's just even hard to imagine this happening. Yet, amazingly, this is what cosmologists discovered that the entire universe is doing. Cosmologists used Type 1a supernovae to precisely measure the relationship between distance and redshift. And in the late 1990s, they discovered that the current expansion rate is actually speeding up and not slowing down. This was a very difficult measurement to make because the size of the effect was small compared to the measurement uncertainties for individual supernovae, and the researchers knew that a result as extraordinary as the violation of one of the key laws of physics would need extraordinary evidence. Nevertheless, the result was corroborated with measurements by two independent teams of researchers. Here is a summary figure that shows the results from both teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, combined with more nearby measurements from the Kalan-Tololo survey. This figure shows the brightness of supernovae as a function of redshift, brightness along this axis, and then redshift along this axis. In this case, because these observations are extending well beyond the local universe, the redshift is now expressed as a fraction of the speed of light rather than as a velocity. The individual points are individual supernova measurements, and the lines represent the expected relationship between brightness and redshift for different models of the universe. That is, these lines that extend approximately diagonally across the diagram. The lines in both panels, from the bottom to the top, show the expected relationship if there were progressively less and less mass in the universe. The less mass, the less the universe slows down, so more highly redshifted objects are further away and thus appear fainter. This is similar to how a ball would rise higher and slow down less if you threw it up on the moon with the same initial speed as a similar ball on Earth. The data show that distant supernovae are even fainter than they would be if the universe had no mass at all in it, something we know is not the case. So the key point here is that this line here, the second from the top, which is labeled an empty universe, is somewhat below the majority of the supernova measurements. This means that the expansion rate of the universe has been accelerating rather than decelerating. For this extraordinary discovery, 3 of the leaders of these teams were awarded the Nobel Prize in Physics in 2011. Measurements of supernovae, along with observations from other studies, have been used to continue to refine our best model for how the expansion rate has changed over most of the history of the universe. Now I will show you the prediction of how the expansion rate has changed that agrees with supernovae and other studies. This figure shows redshift along the bottom axis and the expansion rate along the vertical axis. I've also added the age of the universe along the top axis. We're presently at a redshift of 0, and the current age of the universe is about 13.8 billion years. Note that this figure only shows about the last 12 billion years of cosmic history, not all of it. The expansion rate after about 2 billion years after the Big Bang, had decreased to about 80 kilometers per second per megaparsec. And it continued to decrease until about a redshift of 0.5, when the universe was about 8.6 billion years old, about 5 billion years in our past. This behavior, this gradual decrease in the expansion rate, is what we expected from gravity. The gravitational pull of the mass in the universe is slowing down the universe's expansion rate. Then you can see on this diagram that the expansion rate has been increasing since about a redshift of 0.5 over the last several billion years. This increase is cosmic acceleration. The expansion rate steadily rises to the present value of 0, where it is a little bit less than 70 kilometers per second per megaparsec, which is equivalent to the Hubble constant. This increase is the big mystery. What could be causing the universe to literally defy gravity? One immediate suggestion was Einstein's cosmological constant. Einstein included a cosmological constant alongside his theory of gravity in 1917, because at the time, the widespread belief was that the universe was static. Einstein knew that a static universe required something to counteract gravity, just like we know that a ball will not float in midair on Earth without some other force to counteract the gravitational attraction between the Earth and the ball. Einstein, however, threw out the cosmological constant upon the discovery of the expansion of the universe in the late 1920s. But the discovery of cosmic acceleration does require something to counteract gravity in a similar way. But an important point I want to make is that while adding a cosmological constant to Einstein's equation does successfully produce the acceleration, it does not say at all what the cosmological constant physically represents. So what is it? Well, the short answer is easy. We don't know. And this is why we built the DESI experiment. A somewhat longer answer, however, and hopefully a more satisfying one, is that there are lots of really interesting and plausible ideas. Interesting because no matter what the explanation is, it will expand our knowledge of the physics of the universe. One proposed explanation is that there is some property of space itself that exerts a negative pressure that works in the opposite sense to gravity. In the language of general relativity, there is some intrinsic energy density associated with the vacuum of space that acts like a negative pressure. This is commonly referred to as dark energy because, just like in the case with dark matter, we do not see it. Although unlike dark matter, it is causing an increase in the rate of expansion, not decreasing it. But what is dark energy? There is a plausible route to a solution, to an answer to this question with quantum field theory, yet the estimates from quantum field theory overpredict the value of the cosmological constant by a huge factor, huge even by astronomy standards. The next figure shows an artist's conception of what the quantum realm might look like. Only an artistic rendition of the quantum realm is possible because quantum fluctuations are predicted to be present on such small scales that they are not directly observable. They are as small compared to the size of the atom as the atomic scale is to us. How do we figure out what is causing the expansion? Well, we first need hypotheses that we can test with data, as that is the cornerstone of science. If an idea can't make predictions that are shown to be accurate, it is not elevated from a hypothesis to a scientific theory. In the case of dark energy, there are two main hypotheses. One is that dark energy is a generic property of spacetime. That is, it is a true cosmological constant. This means that the more the universe expands, the more space there is, and the more negative pressure. This makes a very specific prediction for how cosmic acceleration should change over time. The second option is that dark energy is due to something else, like a new force of nature. We already know of four fundamental forces of nature: the strong and weak nuclear forces, the electromagnetic force, and gravity. So this hypothetical fifth force is commonly called quintessence. Many scientists have hypothesized that quintessence could explain cosmic acceleration. Unlike a cosmological constant, the impact of quintessence probably changes with time, and therefore these models predict a different distance redshift relationship. There is a third explanation as well, and that is that there is some modification necessary to Einstein's general theory of relativity. A very simplified version of this idea is that gravity changes from an attractive force to a repulsive force on very large scales, where large is even larger than the several million light years of the largest galaxy clusters. There is some possibility that a modification to general relativity could explain cosmic acceleration, although this explanation was challenged by observations that showed gravity waves travel at the speed of light. Yet even if modifications to gravity do not explain cosmic acceleration, cosmological observations, such as how galaxies move relative to one another on very large scales, are a great way to test hypotheses for other modifications that have been proposed to the general theory of relativity. All three of these ideas are really exciting, and what we need are more tools and more data to test them. At the moment, the best data we have come from measurements of galaxies and quasars, supernovae, and the cosmic microwave background. I am going to focus now on one specific tool, a standard ruler called the Baryon Acoustic Oscillation Scale, or BAO scale for short, as that is the main tool that the DESI project will use. The BAO scale is a relic from very long ago, only thousands to hundreds of thousands of years after the Big Bang. At that time, the universe was so hot and dense that light and normal matter were constantly interacting in what is called a photon-baryon fluid, where baryon is a word that describes most normal matter. One way to picture the universe at this early time is to try to picture the interior of the sun, except that this was what the entire universe was like. After you think about this for a little bit, you will probably be glad that we are 93 million miles from the sun. While the universe was still really hot and dense at this early time, waves propagated through this fluid, somewhat like sound waves propagate through the air. All of these waves traveled at the same speed, and they traveled until the universe suddenly became low enough density that the photons and baryons decoupled, and the waves all stopped propagating. This happened about 375,000 years after the Big Bang. The waves left a very slight excess of normal matter at a distance of about 150 million parsecs from all other excesses of matter in the universe, such as galaxies, while the photons became the cosmic microwave background. There are three aspects of the BAO scale that make it so useful for cosmology. The first is that we can measure it very precisely with the cosmic microwave background, which gives us a measurement back when the universe was really young, when it was about 375,000 years old. That's what's illustrated on the left-hand side in this graphical illustration. The second is that the BAO scale hasn't changed since then. So it is truly a standard ruler. And the third is that it is a huge ruler, about 150 million parsecs across, or nearly 500 million light years. For comparison, the distance to the Andromeda galaxy, the nearest large galaxy to us, is only 2 million light years. However, there is a disadvantage too. The BAO scale is not easy to measure. There's no giant ruler in the sky that one can take a picture of. The first measurements of the BAO scale were only reported in 2005, with a lot of work from two large independent teams of researchers. One team used a sample of 50,000 galaxies, and the other with an even larger sample of over 200,000. That's a lot of galaxies. Both of these are huge samples, and that was just what was necessary to detect this cosmic ruler. Over the last 20 years, the largest spectroscopic survey collecting these data has been the Sloan Digital Sky Survey, or SDSS, which uses this 2.5-meter telescope in New Mexico. As of this year, SDSS has measured over 3 million redshifts, which took about 2 decades. SDSS has managed to do this because they observed many objects at the same time, up to 1,000. They use metal plates that are custom drilled with up to 1,000 holes to match the pattern of stars and galaxies that have been chosen for study. Then a scientist aligns a fiber optics cable in each drilled hole, and the other end of that fiber optics cable directs the light into a spectrograph where the data are recorded. This figure shows an SDSS scientist aligning fiber optics cables with one of the plates. To observe over 3 million redshifts in this way required many, many thousands of these plates, and observations of many of these plates every night for 2 decades. With these millions of redshifts, SDSS has reached back to measure the distances to objects over most of cosmic history. This figure shows the measurement of the BAO scale in 7 samples of objects from the local universe to beyond redshift 2. The horizontal axis is redshift, and the vertical axis is the ratio of the SDSS distance measurement to the best model prediction with a cosmological constant. The smaller panels show the slight excess that represents the BAO signal in each sample. So these points represent the ratio of the measurement to the prediction of the cosmological constant model, and they show that they are generally in agreement with a value of 1 that indicates that these data points match the data. And then these smaller panels show the actual measurement of this small excess present at the BAO scale. These are in units of H inverse megaparsecs, where H is the Hubble constant divided by 100 kilometers per second per megaparsec. So for the current value of a Hubble constant, these correspond to about 150 million parsecs, or about 500 million years. The data here very strongly support cosmic acceleration. While they do not show evidence for time variable dark energy, nor for modified gravity, the absence of such evidence is not evidence of absence. We need much more data in order to test these hypotheses. And that is why I, and a few hundred other scientists and engineers, have worked to build the dark energy spectroscopic instrument. Our aim is to measure the BAO scale with about 10 times as many galaxies and quasars, 35 million of them, and to complete the survey in only about 5 years, rather than 2 decades. DESI is planning on doing this with the Mayall telescope that I showed on my first slide. Now I'd like to show you a picture of it from inside the dome. Similar to the Hale telescope, the Mayall telescope is a reflecting telescope, just with a 4-meter diameter primary mirror, and light from distant objects is reflected off of the primary mirror towards a focus far above it, in this case about 12 meters above the primary. And at the prime focus, that is where we have our instrumentation and we collect the light from these distant objects. The DESI project has added a lot of instrumentation in order to complete our survey. And to show you the different aspects or the different components of this instrument, here's a model of the telescope that summarizes the additions from the DESI project. Some of the highlights are that we built a new, huge state-of-the-art corrector lens system. That's up here at the prime focus. And this corrector lens system has 6 lenses, each of which are about 1 meter in diameter, or a little bit over 3 feet across. So these are very huge lenses. This corrector system then focuses the light from the primary mirror onto fiber optics cables that transmit the light into 10 spectrographs down fiber optics cables. And then our 10 spectrographs are kept at a constant temperature in an environmental enclosure. 2 critical features are that we can obtain spectra of up to 5,000 objects at a time. And we have automated the fiber positioning process so that we can switch to new targets more rapidly. These 2 features are particularly noteworthy because they are why we can observe a larger sample more rapidly than previous surveys. The key technology behind these features is what we call a fiber positioner robot. Here is what one of them looks like. The purpose of this positioner is to place the tip of a fiber optics cable at exactly the right place to collect the light of a distant star, galaxy, or quasar. They are pretty small, similar in size to a pencil in diameter, and the tip of the fiber cable is pointing out from the end. Here's the end of the. They have to be small so that we can fit 5,000 of them in our instrument. This photo here shows just one of them. And the figure in the upper left shows a drawing of the top of one of the positioners, which shows what a photon of light would see as it approached the positioner. Note that the fiber cable itself that we're using has a diameter of only about 107 microns. That's about 1/10 of a millimeter. The positioners work in somewhat the same way as a human arm, just of course a lot smaller. They have one 3 millimeter long arm segment that rotates about the central shaft, somewhat like the upper arm rotates about the shoulder. Then at the end of that part, there is a second 3 millimeter long arm that rotates about the end of the first, somewhat like the forearm rotates about the elbow. The end of the fiber cable is held at the end of the second arm. And this pair of 3 millimeter long arm segments mean that the positioner can place the end of the fiber cable anywhere out to a distance of 6 millimeters from the center, or anywhere within a circle that's 12 millimeters in diameter. Obviously, the reach of one of these positioners is a lot smaller than a human arm, although these positioners are accurate to a few millionths of a meter. My hand is certainly not that steady. The great technology that enables this fiber positioner are very small motors, no more than 4 millimeters in diameter. These have to be incredibly small in order to keep the positioner small. And yet they also have to be strong enough, that is, they have to produce enough torque to move the fiber cable around quickly and precisely. This technology was developed for applications such as insulin pumps, medication delivery systems, and surgical robots. But it turns out to be great for astronomical instruments too. The 5,000 fiber positioners are organized into 10 wedge-shaped structures called petals, and each petal has 500 of the 5,000 fiber positioners. The panel at the left shows one of our 10 petals. This shows both the 500 fiber positioners and the electronics that control it. The middle panel shows the bundle of all the fiber optics cables together that extend from the fiber positioners into our spectrographs. This cable bundle is about 50 meters long. And the photo on the right shows the unit that we put into our spectrographs so that we can record the light from our targets. This is another area where we adapt technology from other fields. The fiber cable we use is the same type of cable used in telecommunications, including to transmit this talk most of the way to your screen. This fiber was developed to transmit light signals extraordinarily well to minimize the number of expensive relay stations. While the light we record is at a somewhat shorter wavelength than that used in telecommunications, the fibers still do a great job of transmitting light from galaxies and quasars from our fiber positioners all the way to our spectrographs. A great new technology from telecommunications is fusion splicing, in which two fiber cables are melted together to produce a new, longer fiber that transmits just as well as if it had been one fiber all along. This was critical for DESI, as it enabled us to combine fiber cables built in the United Kingdom with fiber positioners built in the US without using connectors that would have dramatically impacted our throughput. DESI is the first astronomical spectrograph to use this technology. I took the three photos on this slide when this petal was still at the Lawrence Berkeley National Laboratory in California back in 2018. All 10 petals were installed at the telescope in the summer of 2019, and this next photo shows the process of installing one of them. I really love this photo, as it looks like something out of a science fiction movie. Perhaps a robot performing surgery on a recalcitrant piece of equipment. The surgery analogy is actually pretty appropriate, as this delicate operation positioned each petal to somewhat better than the width of a human hair in the focal plane assembly. Once all 10 petals were installed, all 5,000 fiber positioner robots were finally together. The next photo shows a side view of the ends of the fiber positioners from the summer of 2019. The complete focal plane is almost a meter in diameter, almost 3 feet in diameter. And this photo illustrates how closely the fiber positioners are packed together. If you look carefully, you can just see the change in the pattern at the boundaries of the 10 wedge-shaped petals. The entire focal plane assembly for DESI contains over 500,000 parts, and it is housed in a thermal enclosure that protects it from outside dangers, such as the arch nemeses of astronomical instruments, moths and humidity. Once the light enters the fiber cables in the fiber focal plane assembly, it is transmitted through the fiber optics cables to the spectrographs. And I'm excited to show you what the spectrographs look like, both because they are impressive and because I was very involved in building them. This photo shows our 10 spectrographs in a special climate-controlled room at the telescope. There are many aspects of these spectrographs that make them extraordinary, and in fact, our design for them has already been copied by other projects. One aspect of them is that they include special detectors that have superior sensitivity to nearly 1,000 nanometers, which is critical to measure redshifts for very distant galaxies. Another is that each spectrograph splits the light of the targets into 3 wavelength channels, each of which is optimized for its wavelength range. That is a crucial part of our ability to detect very faint objects. And a third is the use of high efficiency volume phase holographic gratings to disperse the light. A common theme of all these aspects is that every photon from our targets is precious. After they have traveled billions of years across the universe, we want to make sure that they do not go astray in the last few tens of meters before we record them on our detectors. All of these technical aspects were critical to design and build an instrument capable of measuring 35 billion galaxies and quasars in just 5 years, 10 times as many as previous surveys, and in only a fraction of the time those surveys required. I will now conclude with another look at the expansion rate of the universe, but now with forecasts for how well DESI will measure this quantity. This slide shows the same model for how the expansion rate varies with redshift that I showed previously. But I have added forecasts for how well DESI will measure this quantity as blue circles with vertical blue lines that represent the expected uncertainties. These blue points exactly agree with the model because they are just forecasts. They are just a prediction for what DESI will accomplish. What really matters is the size of the uncertainties. That is the size of the blue bars that extend from the points. If our model and estimate of the uncertainties are correct, most of our actual measurements should be within the range of the uncertainties. In addition to the blue points, there are also red squares on the plot. These red squares, with their uncertainties, are based on data, and they are my estimates derived from the latest SDSS results. My estimates do somewhat undersell the results of that survey, as that survey measured many quantities about the universe that this figure does not capture directly. But my key point is that with DESI, we will be able to measure the expansion rate extremely well. I do want to emphasize that the evolution of the expansion rate is only one perspective on the evolution of the universe. And DESI and other surveys measure other important parameters too. These include the amount and distribution of dark matter, the growth of structure in the universe, and the sum of the masses of the 3 neutrino species. While I have focused on dark energy and cosmic acceleration, we do not know what dark matter is either. And measurements of how clusters and superclusters grow over time is an excellent probe of potential modifications to general relativity. While the DESI project was unable to observe for most of 2020 due to COVID-19, we developed new safety protocols and were able to restart at the end of last year. We're presently working on numerous technical improvements and collecting data to validate how we select targets for the 5-year survey. Finally, I'd like to thank you for the invitation to speak today and for your attention. And I would also like to acknowledge the U.S. Department of Energy and other agencies and foundations that have made the DESI project possible, acknowledge my support this year from the Radcliffe Institute for Advanced Study, and say that DESI is grateful to conduct our survey from the land of the Tohono O'odham Nation. And I would be happy to answer any questions. Thank you.
Dr. Paul Martini, thank you very much. Please, everybody, if you would turn on your microphones, turn on your videos, and we can take questions for a while.
Well, okay, I'll ask a question because Bob Buckheim already pointed out in chat the slide just before this one, the predictions for the DESI redshift and distance, the blue and red points. There's a sharp discontinuity in the uncertainties around a redshift of 2, something like that. Yeah, all of a sudden the uncertainties get big again. Why? What's the cause of the relationship between redshift and uncertainty along this curve?
Yeah, great question and good observation. The reason why there is a variation with redshift in the size of the uncertainties, in particular why there is such a sharp one, is the size of the sample that we have to measure the Baryon acoustic oscillation scale at different redshifts. In the DESI project, we actually use 3 different classes of objects to measure the BAO scale. At the lowest redshifts, we use galaxies called Luminous Ray Galaxies. And so these are kind of like, these include elliptical galaxies, lenticular galaxies, generally galaxies that are dominated by an old and red stellar population. And they're very luminous, hence Luminous Ray Galaxies. We can observe those with DESI pretty well up to a redshift of about 0.6 or 0.7, maybe close to, and we can detect the most luminous ones out to a redshift of 1. Then we detect, and we primarily use emission line galaxies out to about a redshift of 1.6, 1.7, as well as a combination of, we also use quasars up to about this redshift range as well. And then starting at a redshift of 2, actually our main cosmological tool switches to using something called the Lyman alpha forest, which is using not individual galaxies as tracers of the baryon distribution, but instead we use the amount of absorption that we can see due to neutral hydrogen in the intergalactic medium. And when we switch from using individual galaxies and quasars to trace the mass distribution of the universe to using the spectrum of individual quasars, we actually suddenly get a lot more information from every object that we are able to take a spectrum of. For a rough estimate is that for every quasar that we observe at these highest redshifts, because we can see a large amount of the distribution of matter between us and the quasar, we get about 50 times as much information from each object. And so that's why suddenly the uncertainties become much smaller. And that's because we're changing what we're using to trace the mass distribution.
Okay, thanks.
I got a question. The optical cables, how often, because there was a slide there that you showed one of the scientists connecting them, is that done on a daily basis, on a weekly basis, or just a one-time connection?
For the Sloan Digital Sky Survey, the scientists would connect the fibers onto the plates for every night of observations, and actually there would be a different setup for every field. With the DESI project, we no longer have to do that because we have created these fiber positioner robots that do the same work automatically. And so for DESI, we never touch the fiber cables. That means that we can change between fields extremely rapidly.
Okay.
I have a question about this BAO ruler that you're talking about. There's in the cosmic background radiation, there's a frequency spectrum, a spatial frequency spectrum, or angular frequency spectrum that characterizes that particular background. And is what you are measuring at closer ranges with this instrument the same, that frequency spectrum, and inferring that the spectrum must be characteristic of the scale?
What we measure is a slight excess in the distribution of galaxies, or the distribution of normal matter in the universe relative to massive objects in the universe. And so one way to think about this is in terms of how likely it is, or how randomly or not galaxies and mass are distributed throughout the universe. In if
that is to say that this distribution across the universe is kind of white. There's no spatial frequency content to it. Is that what you're saying?
Well, the spectrum of the matter distribution is not it's not white because of gravity, right? So gravity causes objects to naturally move together, both to form individual galaxies and then also to form clusters and then even larger structures in the universe. So the distribution of matter in the universe is not random. And then the BAO scale is a small tweak on top of that produces a slight excess of galaxies at the very specific distance of the BAO scale relative to distances that are slightly larger or slightly smaller. So for example, I could go back to the figure that I showed with the SDSS results. And what this is showing is that there is a small excess in the number of galaxies at one very specific separation relative to separations that are somewhat smaller and somewhat larger.
And that
is
excess
the relic of the BAO scale.
And so that excess, the spatial frequency that excess occurs at is indicative of the scale of the universe at that range.
This scale is saying that there is a higher probability of finding two galaxies or two gas clouds with baryons in them at a specific separation of 150 megaparsecs.
Right, so that's a peak in the spatial frequency spectrum.
Yeah, and it's a higher probability of this one particular distance relative to distances that are slightly larger or slightly smaller. And that physical separation is constant over the whole range of the universe, over the whole age of the universe. And if we can measure the angular size of this separation at any redshift, then we can use that to infer what the distance is to that redshift. That's how we measure the distance redshift relation.
This is really
there
interesting. Oh, go
Is
ahead.
there already a plan for how you select targets? Do you already know what your targets will be, or will you survey pretty much the whole sky and select targets kind of on the run, on the fly?
We actually conducted a very extensive imaging survey of the Northern Hemisphere sky that are called the legacy surveys. And we actually just released the latest analysis of those imaging data just a few weeks ago to coincide with the winter meeting of the American Astronomical Society. And we conducted this imaging survey in order to have good enough data to select targets for the DESI project. Even though we're observing 35 million galaxies and quasars, that's actually only really a very small fraction of the objects that we could target to our sensitivity limit. And so we have to be extremely careful about how we select objects so that we can be sure that we select a good representative sample of them at all of the different redshifts we want to study. So a lot of work over many years has gone into developing good algorithms to detect, to select targets, to be sure that we will meet our survey objectives. And we're using the legacy survey imaging as our sample to run our target selection algorithms. And the period that we're in now is basically just double checking that the methods that we have refined over the years will work with the actual DESI instrument.
And will you visit those targets more than once or just one time?
It depends upon which target. For the quasars at the highest redshift, they are quite faint, and it really benefits us if we can obtain a better spectrum of those quasars to better study the amount of absorption in the intergalactic medium. And so those targets will be observed up to 5 times during the course of the survey. That's about 1 million or so of our targets. The other targets we will generally just observe 1 time, and we should get enough sensitivity within just 1 observation to measure the redshift of the target, which is all that we really need to know about them in order to do our science program.
I have 2 questions. From your equipment setup, it looked like the 4-meter telescope is dedicated to this project. It doesn't seem like it's something you'd remove from the telescope so that it could do other missions. And number 2, assuming you get all the data that you're looking for within the 5-year duration, would there be an advantage in extending this project, say for another 5 years or some other time? It doesn't appear that the basic measurements the physical measurements would change. But on the other hand, you could take more measurements of different objects or refine the data somehow.
Yeah, that's right. So to answer your first question, the DESI project or the DESI instrument will not be swapped out with other instruments for other projects. It is as permanently attached to the telescope as any instrument can be. It would be a very extensive ordeal to try to remove it. And actually, we changed the whole top end of the telescope as well in order to install the DESI instrument. So it would require a substantial operation to even retrofit the telescope so that it could support the previous set of instruments. And the reason for that is because in order to conduct the project, we needed all of the dark time that was available at the telescope, and actually we're using the gray and bright time when the moon is closer to full. We can use that as well for conducting a lot of our survey. And so we were able to negotiate a deal to use all of the available nights. And then with regard to what we do in 5 years, there's still a lot of discussion about what will happen. In 5 years, we anticipate that the DESI instrument will still be the largest and potentially most powerful spectrograph that exists. And while we'll have completed our primary science program, there are plenty of targets that we won't have observed. And we're already starting to look into other ways to select objects that would let us conduct an additional survey that would give us better insights. So for example, if we go back to the, let me see, go back to the, sorry. So for example, in this figure, I showed that there is a variation in the uncertainties in how well we can measure the expansion rate at different redshifts. And so we're looking at ways that we could select targets to increase our sample size at the very highest redshifts where our uncertainties are projected to be larger. And then also in this redshift range here where we have larger uncertainties so that we could better measure the cosmic expansion rate, but with very specifically tuned target selection. And so the collaboration is already starting to explore some possibilities.
So I was curious about when you use fiber optic cables, do you lose many photons in the process, or is the efficiency quite high?
The efficiency is very high. We lose some at the bluest wavelengths that we're studying, or at least that's where we have the most attenuation. The fiber optics cables in telecommunications are typically telecommunication signals are around 1,000 microns or even longer wavelengths.
Okay.
And 1,000 microns is about at our maximum. So we're using them at a somewhat shorter wavelength than what the fiber cables are commonly used at for the telecommunications industry. However, the fiber cables are still extremely good, and we have special coatings on the ends of the fibers to ensure that we have very minimal losses of light as photons enter and leave the fibers.
And transition, yeah. So hopefully won't reduce your resolution or your accuracy of the measurement. All right, thank you. It's very interesting. Thank you.
How long do you need to integrate to get enough signal to noise that you are shooting for, and what sort of magnitudes do you think it will reach?
Yeah, good questions. The typical exposure time is going to be on the order of 15 to 20 minutes. We have brighter sources that we will be able to measure redshifts for in maybe as short as 5 minutes. But our typical exposure time is going to be on the order of 20 minutes. And then we anticipate that we're aiming to have about 2 minutes of dead time between when we complete one exposure and start another. So we're trying to have we want to use the nights as efficiently as possible. And then as far as the faintness of our sources, we're aiming to observe sources as faint as 23rd magnitude, or maybe even slightly below that. We should at least be able to detect certain classes of objects that are that faint.
Pretty faint.
Yeah, we spent a huge amount of effort on making the instrument as sensitive as possible to really make sure that we didn't lose any photons in the actual instrument. So we have a very high measured throughput through the whole instrument.
Other questions? Other questions? Well,
will there be, you think there will be any, well, there will be an input to it. That the Hubble constant has been a kind of a source of disagreement for a long time, or from different methods of measuring it, I assume. Will this be a definitive solution to that, or will it be another point on the uncertainty, or will it, or is it because there's a reversal that there's uncertainty?
Well, the current controversy about the Hubble constant is in relation to what the present value of the expansion rate is. And those measurements vary by several kilometers per second per megaparsec. And there are the current difference that exists is between measurements of the Hubble constant that basically measure it the same way that Hubble did, using measurements in the local universe of what the expansion rate is now, and measurements that use cosmological methods similar to what DESI will, or like what DESI will do and what the Sloan Digital Sky Survey has done, which have mapped out the acceleration or the expansion rate and how it's changing over time, and then projected that to what the current value of the expansion rate should be. And those results are currently somewhat in tension with one another. And it is certainly our hope that the new measurements that we will get from DESI will either show that actually that modest discrepancy will go away, or maybe it will show that there really is a discrepancy that would point to something interesting happening in the universe. I'd say the current disagreements are at the level where they are plausibly explained by some combination of statistical and systematic errors. But as those uncertainties are better and better understood, then we should learn whether or not there's some interesting new physics going on, or that the agreement actually is better than previously thought. So I'm pretty excited about that possibility as well.
Yeah. Thank you.
On your 10 spectrographs, each one of which is fed by what, some 500 fiber individual fibers or something like that. Can you register a spectrum from each one of those fibers simultaneously? Or do you, that's what I'm thinking, because that's the way one of those drilled plates would work.
Yes, with our fiber positioner robots, we position all of the fiber cables for all 10 spectrographs in one observation. So each spectrograph records 500 distinct spectra. And so for every exposure that we take, we are measuring 5,000 spectra. Yeah, and that's 5 times as many as the next largest, as the current largest spectrographs that exist.
Would you think that this instrument would be a prototype for even larger spectrographs that you could put on even larger telescopes?
I think it would be, I think it's, you know, I guess as an optimist and an instrument builder, I think it is inevitable that we will have even larger spectrographs in the future. And I do know that there are people who are already thinking about how to build a spectrograph that could observe 20,000 objects at a time or even more. The key technologies that we really need to overcome in order to do that are to make positioners even smaller than they currently are. And that's a big challenge because it's hard to make motors that are smaller than the ones that we're using that would still have enough torque to actually move a fiber cable around and then hold it in place precisely. And so there is currently technology development going on that would do that. Also, another challenge is building larger optics as well. Our lenses for the corrector are already a meter in diameter, so they are as large as the largest refracting telescopes ever built, the Yerkes refractor. That's basically what our corrector lens is like, and so making even larger lenses than that becomes more of a challenge, because then the lenses get so large that they can potentially be sagging under their own weight, and it's hard to maintain a figure. So there are challenges in scaling up, but there are exciting challenges, and there are lots of smart engineers in the world.
Thank you.
Well, we are getting along in time. We've been at this for about an hour and a quarter. I guess if I could conclude with one question, Paul. You outlined three possible alternatives, 3 scenarios to explain cosmic acceleration. Which of those 3 do you prefer?
It's a That's a tough question. I try to approach this from being very much a data driven. I don't want to bias the way I look at the data by having a preferred outcome. There's been actually a lot of research into how to conduct scientific analyses and to really try to develop one's scientific analyses in a way that do not bias the result that one is that are not biased by the result that someone would expect. I mean, I think of the three, I would say that the possibility of a time variation in the dark energy and thus something like a new force of nature, that just seems very exciting. And I think it's something that we could potentially measure and use measurements from an experiment like DESI to really try to figure out what that additional force is. It's harder to see how we would go forward if we measure that the universe is consistent with having a pure cosmological constant, because it's hard to come up with a good explanation for producing something that is so constant. I think modifications to general relativity, though, are also extremely fascinating, and it's certainly possible that more than one thing is happening. So there's no reason why we couldn't have a universe with some modification to general relativity in addition to another force of nature. Although I do know well of Occam's razor, and having one extraordinary explanation is certainly plenty to keep things exciting.
Well, wow! Thank you for that. Thank you.
Thank you very much for inviting me to speak. I really enjoyed it.
Well, Dr. Paul Martini, we appreciate it. Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
It's now started snowing up here really hard. I don't know how long this is going to last.
It's getting a lot
Beautiful
brighter
background.
behind you.
Huh?
Yeah, beautiful background.
Well, it's staying below freezing. So anyway, 2 weeks from now. 2 weeks from now. Wonderful. We've got a special presentation. Timothy Thompson will be talking about Mount Wilson Observatory and the birth of modern astronomy. Tim? We lose Tim. Tim.
Okay, there. Now can you hear me?
Yep.
Good. Yeah, it's basically what I'm going to do is talk about the scientific history of the observatory. You won't hear much about the fancy characters and the usual historical anecdotes, because there's so much science that was done at Mount Wilson that it's really over the top. And I'll probably talk too long. I always do anyway. So just bring your lunch or something.
We are all looking forward to it. And with that, I want to thank everybody for attending. We had a good crowd today. Again, thank you, Dr. Martini. And with that, I will end the meeting. There are no other questions. Right?
Bye-bye.
Bye-bye.
Thank you. Stay safe.
Be safe.
Yeah.